Hello friends, today I am going to give you the concept of analysis of algorithms in computer science. This is Professor Rakesh Kumar Katare of Department of Computer Science at APS University, Rewa, Madhya Pradesh. The matrix multiplication can be represented in the following manner. Cij is equal to Aik into Bkj. Here Aik is the element in the ith row and k column. Bkj is the element in the kth row and jth column, and Cij represents the element in ith row and jth column. The matrix multiplication algorithm is the row measure order. Aik is A11, A12, A13, A21, A22, A23, A31, A32, A33. This is a 3 cross 3 matrix. Bkj is B11, B12, B13, B21, B22, B323, and so on. In same way, Cij is this. Now, matrix multiplication. This is matrix multiplication. Now, matrix multiplication can be represented like this also. The first row will be multiplied with first column. So C11 will be A11 into B11, A12, B21, A13, B31. So the first row A11, A12, A13 will be multiplied by the first column B11, B21, B31. The first row again will be multiplied by second column. First row, second column. Then first row will be multiplied by third column. The first row will be A11, A12, A13, B13, B13, B23, and B33, B13, B23, B3. In this manner, we got C11, C12, C13 means first row of the C matrix. Same way, the second row will be multiplied by first column, second column, and third column. The second row will be multiplied by first column, second column, third column. Same way, third row will be multiplied by first column, second column, third column. So same way, we will get C31, C232, C33. Now here we have to see that how many operations this matrix multiplication will take. So we have 9 assignments: 1, 2, 3, 4, 5, 6, 7, 8, 9. So total operations, the first one is the assignment, which is 9. Multiplication: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the multiplication is 27. Addition: 1, 2, 3, 4, 5, 6, 7, 8, 9. 10, 11, 12, 13, 14, 15, 16, 17, 18. So total addition 18. Therefore, the whole matrix multiplication algorithm or multiplication will take 9 assignments, 27 multiplications, and 18 additions, which include when these 3 types of operations will be added, we will get 54 operations total. Now this can be represented like this. Each row contains 1 assignment, 2 additions and 3 multiplication. So 9 rows contains the following operations. First, assignment 9 row into 1 operation, so 3 into 3, which is n square. Additions 9 into 2, so 2 into 3 into 3. Multiplication 9 into 3 means 3 into 3 into 3, so n cube, because n is 3. This matrix is of 3 cross 3, which is n is equal to 3. Total operations will be 9 plus 18 plus 27, which is 3 square plus 2 3 square plus 3 3 cube, which is n square plus 2n square plus n cube, which is 3n square plus n cube, which is 54. So total operation is 54. The following is the matrix multiplication algorithm. For I is equal to 1 to n, do. For j is equal to 1 to n, do. Sum 0. Initialization of the counter sum starts from sum is equal to 0. For k is equal to 1 to n, do. Sum is equal to sum plus aik into bkj. Sum will be stored in Cij. Let n is equal to 3. Now let us dry run the above matrix multiplication algorithm for n is equal to 3. Because this matrix multiplication is row measure order, therefore I will go from 1 to 3. Same j will go from 1 to 3 and k will also go from 1 to 3. Sum is equal to sum plus aik into bkj. This is a counter. Now let us take some explanation of this counter. Example of counter. Let us take an example. S is equal to s plus 1. Let s is equal to 0. This is initial value, s is equal to 0. Initially, then the old value of s will be added to the new value of s. S is equal to 0 is the initialization of the counter, same as s is equal sum is equal to 0 is the initialization of this counter. So s is equal to s plus 1 is a counter. This is not an algebraic equation because s is equal to s plus 1, s minus s is equal to 1, 0 is equal to 1 is a wrong explanation of s is equal to s plus 1. It is a counter, therefore it is an assignment statement. Assignment statement means we are going to use the memory location s. Initially memory location s contains 0 and then I will add 1 to memory location s, so we will get s equal to 1. Second time the old value of s is 1, means memory location s contains 1, then I will add 1 to the memory location s, then this will become 2. Next time in 2 I will add 1, it will become 3. So what we are doing, we are adding 1 to the old value of s to form a new value of s. So the explanation, because s is equal to s plus 1 is a counter, not a algebraic equation. S is a memory location where in each execution 1 will be added to old value of S to form a new value of S. A table that usually has a k-dimensional rectangular structure is a one-dimensional array, and Aik, Bkj and Cij are two-dimensional array. In notation, Aik used to denote subscripted or indexed items that are elements of an two-dimensional ordered array in the above algorithm. Aik is sometimes used in preference to a doubly subscripted notation like Aik. Same way, suppose we have n quantities v1, v2 up to vn. Instead of writing vj for the jth element, the notation vj is often used. In the above example of matrix multiplication, we have considered the case of n cross n square matrix. In this two-dimensional array, each node Aik belongs to two linear lists: the row I list ai1, ai2 up to ain, and the column k list a1k, a2k up to ank. These orthogonal rows and column lists essentially account for the two-dimensional structure of a matrix. Similar remarks apply to higher dimensional array of information. The point 1, 2 and 3 shows the structure relationship between the data elements in row and column of a matrix. Therefore, computer programs usually operate on tables of information. In most cases, these tables are not simply amorphous masses of numerical values. They involve important structural relationships between the data elements. In its simplest form, a table might be a linear list of elements when its relevant structural properties might include the answer to such questions as which element is first in the list, which is last, which element precedes and follows a given one, how many elements are in the list. All above questions explore the structural relationship between data items. Now, how this algorithm can be run? I will take I is equal to 1, j is equal to 1, sum is equal to 0. Then I will take k as 1 to execute this statement. Then k is equal to 2 to execute this statement. Then k is equal to 3 to execute the same statement. 3 times I will execute k to get C11. 1 time multiplication, 2 time multiplication, 3 time multiplication and 2 time addition, and then 1 time assignment. So all this operations is here. 3 times multiplication 2 times addition 3 times, 1 plus 2 3 times addition in one set of values. So this is row 1 C11. For I is equal to 1, for j is equal to 1, sum is 0, k is 1. First time sum will be 0 plus this, k is equal to 2, sum will be the first one added by the second one, first one and addition second one. K is equal to 3, sum first one, second one and third one. So I get C11 and sum will be stored in C11. So this is row 1. Now how to calculate operations? Let us take assignment. This is first assignment, this is second assignment, this is third assignment, this is fourth assignment, this is fifth assignment. So there are 3 assignments. These 3 assignments will be used for sum and the whole sum will be transferred to C11, and this is initialization of sum. So there are 5 type of assignments we are using. This is first addition, this is second addition and this is third addition. These values are already added. These 2 values are already added in the first 2 steps. Therefore there are 1 addition, 2 addition and 3 addition. Same way, this is first multiplication, this is second multiplication, this is third multiplication. So in the first C11, in this part of the algorithm, assignments takes 5 operations, addition takes 3 operations, and multiplication takes 3 operations. Same way, second row I will get from the same part of algorithm by changing the value of j is equal to 2 and k again 3 times. Next time j is equal to 3, same value I will get C13. Next time the value of I is equal to 2, j is equal to 1, first part as C21, I is equal to 2, row 5th, C22, I is equal to 3, 6th row C23, same C23. Now I is equal to 3, again j is equal to 1, same part I will execute to get C31. 8th row j is equal to 2, I will get C32. 9th row j is equal to 3, sum again I will do the same thing to get C33. So in this algorithm, total assignments will be for assignment takes 27 operations. 27 operations. Addition takes 27 operations. Multiplication takes 27 operations. Cij takes 9 operations. Sum takes 9 operations. Now let us observe again. Now observe again this part of algorithm. We have 3 operations, this assignment. 2, 1 for initialization and 1 for sum to be transferred to C11. There are 9 part of this, starting from C11 to C33. There are 9 elements. So 9 initialization, 9 transfers, and 9 into 3, 27. So 27 plus 9 plus 9. Same way, 1 addition, 2 addition, 3 addition. So 3 addition means 1, 2, 3. So 9 rows means 9 into 3 is 27. Same way, 3 multiplication, 9 into 3 is 27 multiplications. So again, assignments n cube, addition n cube, multiplication n cube, Cij n square, sum n square. Therefore, total will be 3n cube plus 2n square. So original matrix multiplication without writing algorithm takes 3n square plus n cube operation, whereas when we are writing algorithm, then operations will be 3n cube plus 2n square. The difference will be calculated like this. 3n is, you will get 2n cube minus n square. If n is equal to 3, there are 45 extra operations. Now what are the extra operations? Let us see. There are 27 assignments. So 9 extra additions are there. Same way, 0 multiplication, C assignment of sum in Cij is 9, they are extra. Same way, sum is equal to 0, it is also 9. Therefore, there are 45. We have extra assignment in our algorithms, which is required to complete the intermediate calculations. Note the following in matrix multiplication algorithm. The variables will be I takes n assignments, J takes n square assignments, C takes n square assignments, K takes n cube assignments, sum takes n square plus n cube assignments. Hence, total number of assignments is n plus 3n square plus 2n cube. I is 3 times, J is 9 times, C is 9 times, K is 27 times, sum is first initialization and other sum is 27 times. So total is this. What is time complexity? The sum operation m plus this is executed n times. Hence, time complexity of n is order of n, where on must be called as order of n. Space complexity. The store n integers, we required at least n memory locations, hence Sn is order of n. Space complexity will be dependent on the compiler under which we are going to execute the algorithm or program. For C, integer will take 2, bytes, float will take 4 bytes, long integer will take 4 bytes. Therefore, space complexity will be depending upon the requirement of the compiler. Order calculation. A function fn said to be order of gn if limit n tends to infinity, fn upon gn will be a constant which is not equal to 0. Definition. Fn of is equal to order of gn read as f of n equals big O of g of n if and only if there exists two positive constants c and n0 such that fn is less than equal to c of gn for all n is greater than equal to n0. In other words, there exists positive constant n and k such that fn is less than equal to k of gn for all n is greater than equal to n0. It is denoted as fn is equal to big O of gn. Total assignments in our previous matrix multiplication application were n plus 3n square plus 2n cube. Let fn is equal to 2n cube plus 3n square plus n and gn will be n cube. Clearly, let n tends to infinity, fn upon gn is equal to limit n tends to infinity 2n cube plus 3n square plus n upon n cube, which is limit n tends to infinity 2 plus this value which is equal to 2, which is a constant which is not equal to 0. Hence, matrix multiplication algorithm is of order of n cube. Thanks.